Now our next theorem states that if f is a function, then the converse, the relation you get when you reverse the xy elements of each ordered pair, itself is a function if and only if f is a one-to-one function. And in this case, the domain of f is the image of f hat, and the image of f is the domain of f hat. Now let's think about what this theorem is saying. Let's say that f, this is A and that's B, say, and f maps all of A into B. Well, suppose that f was not one-to-one. In other words, suppose that f maps little a and little b to the same value z in the set B. That's legal for a function, but not a one-to-one function. This function is not one-to-one. And notice that f hat goes the other direction. It starts here and it ends up over here. So you have z as a first element and you have b as a second element. You have z as a first element. You have a as a second element. That's not even a function. So it needs to be a one-to-one. F needs to be one-to-one in order for f hat to be a function. So what we end up with is so I should go both directions maybe. Let's do the f there. F hat. That's A, that's B. So now, f will map this little a over to this little b. This is the domain of f, that's the image of f. If we start over here, then this f hat will map little b back to a, and b comma a is the ordered pair in f hat. And something that we're all familiar with is an inverse function, and that's what we've been leading up to with this definition of converse. If a function g is one-to-one, if I didn't mention it, this is my abbreviation of one-to-one. If the function g is one-to-one, then g, which looks like a -1 exponent, is the inverse. Of g. And also, g inverse is a one-to-one function. I frequently will draw functions that are one-to-one. I try to make them obviously one-to-one. I'll do something like, if that's A and B, I'll do things like this. I'll make it look like that it's obvious where each element over here gets mapped to one single element in the right-hand side, and also the inverse that maps each one of these into each element in this set into an element in that set. So I kind of make parallel lines to make it look like it's a one-to-one function. Okay, well, let's suppose that a function f maps A into B. And some set W is a subset of the domain A. Well, this set, f of w, remember w is a subset of that, of A. It's the set of all f of little w such that w is in big W. So it may look something like this. If that's the set A and that's the set B, W could be this set right here. This set that I filled in. Well, it may map only to these elements in set B. This would be f of W, just that region. It's called the image of the set W under the function f. It's the image of the set W under the function f. Another related term is if C is a subset of B, over here, this is the codomain of F, then F inverse of C is equal to the set of all A in capital A such that f of A is equal to, f of A is an element of big C. That's called the inverse image of C under the function f. Function f, this is the function f inverse, so this is the inverse image of C under f. So it's a set of all elements in A. Let's say this is C. And maybe all of these elements map to those. All of this would be f inverse of C right here. And the definition, this is interesting because the definition f inverse of C doesn't really even require that f be invertible. It simply says if you're an element in this set B, this big set B, that gets mapped to from A, then you're in f inverse of C. Well, I've mentioned a one-to-one function already, kind of explained what it meant. I'm going to formally define it now, and more than that actually. If the function f, which goes A into B, is one-to-one, I guess what I'm defining here is the term injective, or f is an injection. I'm going to say if f is one-to-one, then f is an injection. I hope that shows up. This word I'm defining is injection. I'll move to the left a little bit. F is an injection. You could say that f is an injective function. If the image of f is equal to B, and what does that mean? That means that every element in B is mapped to from some element in A by the function f. In that case, then f is a surjection. And we typically call that an onto function. That means that it maps from A onto B, means that every element in B gets mapped to from the set A. If f is both an injection and a surjection, then f is a bijection. frequently we'll say that f is 1 to 1 and on 2. That's synonymous with f being a bijection. So pictorially, if we have A here and B here, and F maps f of A is equal to just this section down here inside of B, that would not be an onto function. Because there's an element out here, you could call it little b, that does not get mapped to. So that's not a surjection. It's not an onto function. I hope you were able to see that drawing. If not, it looks something like this. So A is mapping only into this subset of B. So that would not be a surjection. All right, well, the next thing, we're still in the basics of functions. If f maps A into B, and G maps B into C, then the composition of G by F is, well, we don't denote it like this. It's not an O, it's not a 0, it's just a small circle. G composed with F, or the composition of G by F, and we write it like that, where it's defined as follows. Remember, this is just a new function, so it's going to be a set of ordered pairs. Set of all ordered pairs x, y, such that there exists, and a reminder that this backwards E means there exists, shorthand for the two words there exists. There exists a B in the set B such that the ordered pair XB is an F, and maybe I'll write it down below here, BY is in the function G. So if we have a picture here, we've got say 3 sets, capital A, capital B, capital C. That's because F maps something from A into B. G maps something from B into C. So I want to be able to take f of g of x, sorry, in this case, g of f of x. So I'll take a little a, let's use the same letters. X has to be in the set A. There has to exist some B over here such that f maps x to B, so that's an ordered pair xb, and there has to be an ordered pair by in the function g, which means there's a b in this set, same b as a matter of fact, that b matches that b, and there's a y right there. So g composed with f is a function that you could say, well, what's the first thing you do? You take x, an element here, and you have to take f of it to get to b. That gives you the ordered pair xb. So then after you do f of x, then you take g of f of x. So let's see, how could I write that? This means f of x equals b. And this means that g of b equals y. Well, that means that g of f of x is equal to y. This is what I think of whenever I see g of f of x. I just write it down as g of f of x. I'm not a big fan of this symbol here. And this was just substitution because b is equal to f of x. So I replaced b with f of x. G of b is here, g of f of x is there. G composed with f of x equals g of f of x. All right, let's continue. We didn't state whether g of f of x was or was not a function. And this theorem will help us out to determine if f maps a into b and g maps b into c, if those two are both functions, if they're both functions, then the composition is a function. And it maps what? Remember that picture? It takes A all the way across to C. Makes a little stop in the middle in the set B and then moves on to C. Then this is a function. Well, we haven't done too many proofs, so let's go ahead and prove this statement. If this is a function and this is a function, then this is also a function. So to prove it's a function, you need to prove that every single ordered pair, well, let me rephrase that. If you have two ordered pairs that have the same first element, it better be that the second element is the same as well. You can't have one element in the left getting mapped to two elements in this set. So what we'll do is suppose that x comma u and x comma v are in the elements of G composed with F. And what we're going to prove is that it must be that u and v are equal to each other. And that will prove that this is a function. Okay, so that means that g of f of x equals u. That's what this means. And then this one means, I'll write it underneath, g of f of x equals v. So both that's what we're supposing to be true, and all we need to do is prove that u is equal to v. And I'm going to write small, but maybe I'll say we must show that u is equal to v. And that's what we'll do. By definition of G composed with F, there exists a B1 and a B2 in B such that the following holds, and we're doing nothing but the definition. X comma B1 is an element of F, and B1 comma U is an element of G. That's just the definition of what it means of G composed with F. You can go back and look at the definition. It means this B1 exists. And the B2 is going to be for V. So X B2 is an element of F, and B2 comma V is an element of G. We've used nothing but the definition of what it means for the definition of G composed with F, the composition of G and F. Well, what do we know now? I'm giving it away here. Since F is a function, we've got two ordered pairs here, both starting with X. That means B1 and B2 happen to be the same number. Okay, and if you want to put the justification in parentheses, you can say, since F is a function. Well, similarly, since F is a function, that is true. And since G is a function, and since B1 and B2 are the same number, we just showed that, these are the same number, that means that U and V are the same. Therefore, G composed of F is a function. And that is the end of the proof. Okay, I wish I had more room. I'm going to erase something and then kind of show pictorially why it's fairly obvious that G composed with F is a function. I'll leave the theorem statement up. Well, we would have either this picture where we have X is in the set A, the only way that we could get that mapped to a U and a V over here, which would be a contradiction, we can't do that because G composed with F is a function. X is only going to get mapped to one of those. But if it were to, the only way that X could map to both of them is that if X mapped to two numbers here, and then these numbers mapped to U and V, but that's a contradiction because F is a function. F can't get mapped to two values in B. Another way that we could check to see if it works, or to convince ourselves that G composed with F is a function, is X, as we suspect, maps to one value there. Call it B. And B maps to two different numbers, U and V. That's the only way X, I think that's about the only other way X could get mapped to two numbers under this function. But this is impossible because G is a function and B can only map to one number in the set capital C. Now, just a couple of notes or observations about compositions of functions, talking about the domains, the images. A note I want to make clear is that the domain of G composed with F is equal to the domain of G of F of X. All I did is said that, I guess I should say F of X, to be consistent. The domain of this function is the same as the domain of this function because this is equal to that. The only numbers you can plug into this are numbers that the first thing you're going to do here is F of X. F of X will give you a new number. and then you plug that number into g. So it might be that you can't plug every single number into this, but it's a, let me say it's a subset of the domain of f. And if, you'll see why it's a subset, if f maps A into B and G maps B into C, then the domain of G composed with f is equal to the domain of G of f of x, which is equal to the domain of f. So in general, where I haven't defined the domains of f and the domains of g, all we can say is that the domain of this function is a subset of the domain of this function right here. You may not be able to plug every element into it. But if we know, I've drawn that picture before, A into B into C, if we know f maps A into B and g maps B into C, then we're able to say that the domain of g composed with f is actually the domain of the function f. So you can plug every value in that set A, this set A, into this new function, g of f of x. Some subtleties about the domain of functions. Well, a really simple example, just to make sure that we understand what composition of functions means, is if f of x is x cubed and g of x is, say, cosine x, and we define h to be g composed with f, then what is h? Well, we know it's g composed with f, but we know f and g together, so we can figure it out. So h of x is g of f of x. So now I know what f of x is. It's x cubed. I'm going to plug that into g of x. I'll get cosine of x cubed. So this is h of x.